Hi, welcome to this video series. In this video series, we'll learn how to create embedded software applications using STM32 microcontrollers, the STM32 Cube IDE, and the CubeMX code generator. So this will be a project-based video series where we dive into using a variety of microcontroller peripherals through real-world applications. In today's video, we will cover the basics, like we'll learn what exactly is an IDE and how to install STM32 Cube IDE, and we'll get started by programming simple peripherals like GPIOs, working with timers and configuring interrupts. Okay, all right, so let's get started. Now let's discuss which IDE to use for this course. First of all, what exactly is an IDE? IDE, which stands for Integrated Development Environment, is a software. Basically, it's a software that combines various tools and features to support your project development. For example, an IDE may contain all these components, like it may contain the code editor where you can type in your code. It supports, integrated compiler, or you can also configure the IDE to use some other compiler so that you can compile your code. And it also supports debugger so that you can debug your code on the target. And also it supports the inbuilt version control system interface by which you can communicate with your Git account and you can directly commit to your Git repository from the IDE itself. And it may contain other build and automation tools. Basically, it comprises of all these components to support your project development. So everything comes as one software. That's what we call as IDE. For our microcontroller project development, which IDE to use? There are several options actually. The first one is STM32 Cube IDE. This is officially released by ST Microelectronics and ST maintains it, and this is the official IDE for STM32 microcontrollers. But it supports only STM32 microcontrollers. You cannot program any other vendor's microcontroller from this IDE like NXP or Texas Instruments. Those vendors have their own IDE. This course is based on STM32 microcontroller. In this course, I'll be using STM32 Cube IDE as the primary IDE software for this course. We'll be installing this software. Apart from that, I'll also have one section where I will show you step by step how to use the Visual Studio Code to work with STM32 microcontrollers. So there is a plugin for STM32 microcontrollers. You can install that plugin in the Visual Studio Code and you can start working with STM32 microcontrollers using Visual Studio Code. So these two options are, it's quite popular and very easy to use. Apart from that, you can also use Kyle MDK software, which is also a good option, but I'll not be covering any of these options in this course. So you can use IAR Embedded Workbench, or you can just use an Eclipse software with STM32 plugin or Platform IO. I'll be using this as the primary IDE for this course, but I'll also show you how to use VS Code IDE to work with STM32 microcontrollers. Now let's do some software installations. So you have to download and install this software. The first one is primary IDE for this course, that is STM32 Cube IDE. So this is all-in-one IDE using which you can write code, you can compile, debug, you can flash the executable onto the target, and you can do so many things. So all-in-one software. And install this IDE only if your IDE of choice is STM32 Cube IDE. For any reason, if you want to use Visual Studio Code, then you need not to install this IDE. You can watch the next section where I have covered using Visual Studio Code to program the STM32 microcontroller. Then I would also suggest you to install this software, STM32 Cube Programmer. This is not an IDE. This is just a software which communicates to the microcontroller over several interfaces like UART interface, USB interface, SWD interface, like that. Basically, it can talk to the bootloader of the microcontroller to program the microcontroller. A very helpful tool. So it has a lot of capabilities, but this is not an IDE. This is a programmer by using which you can program the microcontroller without using any onboard or off-board debuggers. So if your board supports the onboard debugger, or if you have external debugger connected to the board, then to download the code, you can just use STM32 IDE. You basically don't need the STM32 programmer. But if you don't have any debuggers with you, you just have a custom STM32 microcontroller board which doesn't have onboard debugger, or if you don't have access to the external debugger, then still you can program the board using this STM32 programmer, because it can talk to the bootloader of your custom hardware and it can download the executable to the target board. For that purpose, we'll be installing this software. Now let's download and install this software. Now let's first download STM32 IDE. Just type that in Google and go to the official link of ST Microelectronics, and from here you can download. Just go to the end. From here you can download as per your machine. So my machine is Windows, so I'll be installing the latest version. You can just click on get latest. Let's just accept this license agreement, and then you have to log in to your ST account. If you don't have account, then you have to create an account, or there is another option, download as guest. So you give your first name, last name, and email address. ST will email you the download link. You can do that as well, but I suggest you to create an account to download this software, because when you start using STM32 IDE, and if you want to download any microcontroller specific libraries or hardware abstraction layer files, then ST won't allow you to download any files until you log in to your account. In the IDE, it asks you to log in. That's why I would suggest you to create an account and download this software. So let me log in to my ST account. I just logged in. Now let's download. So now download has started. Let's double click to install this. It would install in this path, and please check these two options. So it will install the ST-Link drivers. Now let's click next and finish. So we just installed the Cube IDE successfully. So now let's install the STM32 programmer. Just type STM32 programmer in Google and again go to the official link of that. And from here you can download the latest software as per your machine and you can install it. I hope you can do that. So in the subsequent lectures, we'll understand how to use this software. So we just installed STM32 Cube IDE, and in this lecture, let's see how to create a new STM32 project using STM32 Cube IDE. Now, first let's launch the STM32 Cube IDE. For that, go to the search box here and type STM32 Cube IDE here, and let's launch it. So when you launch the IDE software, it will ask you to select a particular directory as workspace. Now, what exactly is a workspace? A workspace in STM32 IDE is nothing but a directory. It's just a folder or directory where all your projects are organized or stored along with their associated metadata. So it's just a directory where you store all your projects in one place. So that's what the IDE is asking here. Here in my computer, I have created a folder called STM32 Projects. Under that, I have several folders like documents, and all projects. This is just an empty folder, and I will treat this as my workspace to keep all my projects under this directory. So you can also create similar folder hierarchy. I'll just open this empty folder. I'll just select this path and I will paste here in the STM32 Cube IDE launcher, and let's click launch. Now as you can see, this folder is treated as workspace and the Cube IDE has created a folder named .metadata. Now it is opening the IDE. Now we just launched the STM32 Cube IDE, and here you see various parts of the IDE, and as we make a progress in this course, we will understand all these options. If you want to watch some videos released by ST, then you can go through these links and you can read about various STM32 products. But in this video, our goal is just to create a simple project. Now let's see how to create a new project. Now to create a new project, you have to go to File and go to New. You will be presented with various options. You can create a Makefile based project, or the CMake based project, or the STM32 Cube IDE based project. In this video, we will just select this option, STM32 project, which is actually an IDE based project. So we will just select this STM32 project. Now it is doing some network activities, so let it complete this activity. Let's wait for some time. Now you have to select the target. You have to select what is your target microcontroller or target board. Here you have two options. One is MCU selector and another one is board selector. So you have to select this option if you are developing with a custom board that uses an STM32 microcontroller. Like in our case, we are using a custom board. This is a custom board what we are using in this course. So this is not a board which is officially released or supported by ST Microelectronics. So we are going to use this option in the target selection. And if you are using some standard development board released by ST Microelectronics, then you have to use this option, that is board selector. So this choice automatically configures the IDE to match board's hardware specifications, which includes all the peripheral pin configurations and default configurations. Since in this course we are using the custom board, so I'll be selecting this option, MCU selector. I'm going to use this option, that is MCU selector. Then I'm going to type in the part number of the microcontroller which is being used on the custom board. And the part number of the microcontroller which is being used on this board is this one, STM32F303CCT6. Let's type in that code here. Let me just select that. As you can see here, two items is listed. Let's select this one, and it shows all the details about that microcontroller here. You can right away download the data sheets and other documents from here itself. So let's select that and let's click next. Now let's give a suitable name for the project. I'll call this as 001 underscore. I'll call this as, since it's a simple LED blinking application, I'll call it as LED underscore blinker. That's the name of the project. And after that, here targeted language, select C because we are coding everything in C. So we are not using C++. And targeted binary type, select executable, and the targeted project type. Here, since we are going to use the hardware abstraction layer APIs provided by the ST, so the hardware abstraction layer is called as STM32 Cube, and we are going to use the standard APIs provided by the STM32 Cube. That's why select this option. So if you are not using any hardware abstraction layer APIs provided by the STM32 Cube IDE, I mean, if you are doing some bare metal programming where you are developing your own APIs or you are programming an application, everything from scratch, So then you may select this option that is empty, but that is not the case with this project. So we are going to use the APIs provided by STM32 Cube. Select this option and click next. Here, make sure that in the code generator options, this option is selected, copy only necessary library files. Then click on finish. Here you may press yes. So it will take a while before it completes project creations. Please be patient. All right, so congratulations. We just created a new STM32 project successfully. Now in this project, at the left hand side, as you can see, we have got a couple of folders related to our project. After that, at the right hand side, we have a configuration tool by using which we can configure our microcontroller. We can select what are the ports we want, like we can select the peripherals from using this pinout and configuration tool, and we can directly configure the pins of the microcontroller for the desired functionality, and we are going to explore all these things in a moment, don't worry. But if you look at the left hand side, there are a couple of folders, and we'll see what these folders are. Here I have written small notes regarding the folder structure of the project. Let me briefly explain all these sections. First of all, here this is a project name. You know that LED blinker is a project name. And after that, if you just expand this includes section of the project, it will show you various paths pointing towards various directories. These are called as include paths. Please note that these are the directories that the compiler will search for header files during the build process. That means when you compile the project. These include paths are set up by default when you create a project using STM32 Cube IDE. So these paths are added by the STM32 Cube IDE by default whenever you use standard library header files like stdio.h or math.h or string.h, or when you use device specific or microcontroller specific header files. Those header files will be located in these paths. You need not to give any full path name to include any standard header files. After that, here it contains project specific files, and it also contains a startup code of your microcontroller. So this startup code is actually added by the CubeIDE automatically. You need not to worry about that, and please do not edit this startup code. Don't edit it. I mean, currently we don't have much knowledge about handling the or writing the startup codes. For a time being, we'll consider that these files should not be edited. You can keep all your project files like .c files, .h files in these folders, source and include. This is a place where you keep your main code or main project files. After that, this is a driver section. These folders contain peripheral drivers and SIMSYS files. And we'll understand what exactly is a SIMSYS sometimes later. Don't worry about that. But more importantly here, this HAL driver folder contains the selected microcontroller peripherals driver files. Let me just show you that. For example, if I just go and expand this, as you can see, these are all different peripherals driver files given by the vendor, in this case ST Microelectronics. And you can open that. These are not read-only files, but don't edit these files. Don't write any code inside these files, or don't delete any functions or code from these files. Basically, all these are microcontroller peripheral driver source codes. And after that, there is one file called IOC file, which stands for IO configuration. By using this file, you actually do all the pin configurations. When you open this file, this window will open. For example, as you can see here, If I want to go to this window, I just have to click on IOC file. Let me just double click on IOC file and the IO configuration will open. All the IO configurations, whatever you do here, will be saved in this IOC file. And finally, this is a linker script of the project. And again, this is automatically generated by the STM32 Cube IDE, and please do not edit this file. If you want to know more about startup files and linker script files, you may go through these YouTube playlists created by me. So where I'll show you how you can write your own microcontroller startup file as well as linker script file. For a time being, don't stress too much about the startup file and linker script file. So these are automatically generated. In summary, the startup code, which is typically in assembly or C language, is used to set up the environment for running your application code. These are the tasks done by the startup code. It initializes the data section, copies the initial values for initialized data from the flash to the RAM, and it clears out the BSS section, sets all the memory in the BSS section to 0 to initialize global variables that are explicitly initialized to any other value. It sets up the stack pointer to the top of the stack, and it calls the initialization function of the standard library. Then it jumps to the main function. So that is actually the starting point of your program. The linker script file is used to define where different sections of your program, such as data, code, and the vector table, are placed in the memory of your microcontroller. And you can also use linker script to customize stack and heap settings of your project. So please note that when you are working with STM32 Cube IDE, okay, if you want to download any, ST's microcontroller specific libraries or hardware abstraction layer, or if you want to download any software components, you have to log in to your ST's account by using this login option. So this is very much essential. Okay, otherwise this IDE won't allow you to download anything. It was not there previously, but recently ST has made it mandatory. If you have already registered, then use your login credentials, or you might have to create a new account and then log in. So without logging into ST's account, you cannot download the libraries or hardware abstraction layer driver files related to your microcontroller from ST. Okay, please note this point. Now let's do the first project. Let's do one LED blinker or LED toggling application. The objective is to get familiar with basic GPIO control on the STM32 microcontroller using this STM32 Nano board and use of logic analyzer for observing and debugging hardware interactions. So we'll also use the USB-based logic analyzer to observe the toggling of GPIOs in this project. Basically, goal of the project is to toggle all on-board LEDs of the board at 1 second interval. The hardware requirements for this project is you need to have STM32 Nano board or any STM32 board. It need not be STM32 Nano board. You can use any STM32 board. And these are optional. This is just to observe the toggling of GPIOs. So you would need a logic analyzer and connecting wire. So these are absolutely optional, but I'll show you how to use the logic analyzer to debug the toggling of GPIOs. In later projects, we'll also use this logic analyzer to debug the serial communication protocols such as SPI or I2C or other protocols. And software requirements, you must have STM32 Cube IDE and STM32 Cube Programmer, because STM32 Nano board doesn't have onboard debugger, but it supports programming the board through the built-in bootloader that I'll demonstrate. And for that, STM32 Cube Programmer is required. And then logic analyzer software. This is optional, but I'll show you which logic analyzer software you have to install and use if you have the logic analyzer hardware. Now let's explore the onboard LEDs of the Nano board. Here you see D1, which is an LED, D2, D3 and D4. Basically there are 4 onboard LEDs, but D1 we don't use actually. So D1 is a power LED which is not a user LED, so we don't use this for this exercise. So we'll use the blue LED which is D2, D3 and D4. You can find the LEDs over here. This is a schematic of the LEDs which describes how these LEDs are connected to the microcontroller pins. As you can see here, the D2, the positive terminal of the D2 LED is connected to the GPIO port A, pin number 1 of the microcontroller. So this goes to the microcontroller. Similarly, the D3 LED is connected to the GPIO port A, pin number 2, and this is GPIO A, pin number 3. Now we have to configure all these microcontroller pins in GPIO output mode. Why output mode? Because we are controlling the device here, right? The device is an LED. That's why you have to configure all these GPIO pins to the output mode. Now let's do that using the STM32 CubeIDE peripheral configuration feature. Now we have our project, and here, as you can see, we just presented with unconfigured microcontroller. As you can see, it looks completely blank. This actually shows a microcontroller in its default format. No pins have been configured so far. First, we will configure the GPIO port A pin number 1, that is PA1. So in the search box, just search for PA1. And as you can see, it will start toggling all the pins which starts with the name PA1. Here it is, PA1. And you just click on that. Then select the option GPIO output. As you can see, this pin supports multiple functionalities like ADC, RTC, timer output channel, etc. Let's not worry about those things. Just select GPIO output. That's it. After that, PA2, which is right here. Let's configure that pin also to the GPIO output mode. After that, PA3, select this to GPIO output. After that, you can check these pin configurations by going through the pinout and configuration section if you want to understand what are the other parameters of these pins. So you can go to the pinout and configuration and go to the system core section, and here go to the GPIO. As you can see, it actually lists all the selected GPIO pins on the microcontroller. And from here, you can change some settings if you want. First of all, as you can see, the mode is set to output. As you can see here, when I select that, it shows other options. First of all, initially, the output level will be low. And initially, if you want output level to be high, then you can change here. That means initially the output level of the pin will be 0 volt. And the GPIO mode. So the mode, you configure this to a push-pull configuration. And for this exercise, let's not activate any pull-up or pull-down resistors. That's why I select no pull-up and pull-down option here. After that, maximum output speed of that GPIO pin, currently set it to low. Basically, this signifies how quickly a GPIO pin can switch between high and low. It controls the slew rate of the pin. So slew rate refers to how quickly the voltage level on a pin can change from low to high or high to low. Currently, we'll set it to low. Then you can assign some label to this. For example, here PA1, it's a D2 LED. D2 LED, that's a blue LED. You can give that label. So I'll just call this as user LED blue. That's it. Then you can go to the next pin and don't change any settings here for this exercise. Just you can give another user label here, like for PA2. I'll just say user LED green. And for PA3, I'll call user LED red. That's how you can manage other parameters of a GPIO pin. Go to the system core here and select GPIO tab. And when you make those changes, as you can see on the right hand side on this pinout view, so it actually takes those labels. Now you may be wondering, what is the clock configuration of this project? I mean, what is the clock speed with which our microcontroller is running in this project? Whenever you are doing any microcontroller project, you must know the speed of the microcontroller or the speed at which the processor or the microcontroller is running. Now that information you can get from this clock configuration section here in the IDE. By using this clock configuration block, it is very easy to configure the desired clock frequency for a microcontroller. So as we make a progress in these video series, I will talk more about configuring microcontroller to the desired frequency using this tool, clock configuration tool. But as you can see here, currently the H clock is set to 8 megahertz. That is actually the main clock of the microcontroller. And from that main clock, other clocks or clocks to the different domains of the microcontroller is derived. For example, as you can see here, this figure mentions something like 2 Cortex system timer, and also it mentions something like F clock, Cortex clock. That means the H clock is fed to the Cortex AM processor directly here, as you can see. That means the Cortex processor, which is there on this microcontroller, also runs at 8 megahertz in this case. I mean, in this configuration. So what is the maximum clock speed you can achieve in this microcontroller? You know that in this board, the microcontroller is STM32F303. And if you check the data sheet or reference manual of this microcontroller, then you will come to know what is the maximum speed with which this microcontroller can operate. And you can also see that this value is also mentioned over here, 72 megahertz. So that's the maximum clock frequency possible on this particular microcontroller, which is sufficient for most of our projects. But I don't want to bump the clock to 72 megahertz for this project. By default, it is actually set at 8 megahertz. So for a time being, let's use this speed 8 megahertz. Please note that the STM32 microcontroller can run using different clock sources like internal high-speed oscillator. There is one high-speed oscillator present inside the microcontroller. Its name is RC oscillator, and it is by default enabled upon reset of the microcontroller. So it is always enabled. I mean, you can disable it, but upon reset of the microcontroller, this clock is enabled. What is the value of this, or what is the frequency of this oscillator? To know that, you have to refer to the microcontroller's data sheet or reference manual. And in our microcontroller, that is STM32F303, its value is 8 megahertz. After that, STM32 microcontroller can be given external clock using a crystal oscillator that we call as external high-speed oscillator. So this is like, connecting a crystal oscillator to the microcontroller pins to supply the clock. And the STM32 microcontroller can also be configured to use the clock generated by the PLL engine, which stands for phase lock loop. This is again internal to the microcontroller, and it is capable of generating higher frequency clocks using the base clocks such as HSI or HSC. All these three different clock sources you can identify here. For example, as you can see here, there is a multiplexer here. So there is a HSI, which is by default selected, and also there is HSC, and also there is PLL clock. This PLL clock is generated by this PLL engine. For this exercise, let's not worry about all these terminologies. So let's just use the internal RC oscillator of the microcontroller, that is HSI, whose value is 8 MHz. For a time being, you need not to do any settings in this clock configuration, so let's just leave at this stage. Now we did some settings here, so let's save it. Let's go to the file and let's click on save. It saved the project, but it is asking whether to generate code for this project or not, because you selected a couple of configurations for these pins, and now the IDE is asking whether the code needs to be generated or not. So we'll click on yes. Let's click yes here, and now it will generate the code. Now the code is generated. So now if you want to check where exactly is the generated code, you can go to the core and go to src folder and open the main.c. In the main function, as you can see, there is one new function call has been added. Currently, remember, we just used only one peripheral in the microcontroller. So that is the GPIO port A or GPIO peripheral. Now, if you want to go to the pinout view, you can click on this IOC file, which opens the pinout details. As you can see in the microcontroller, we just enabled one peripheral. That's why there is only one function call, which is used to initialize the GPIO peripheral or GPIO pins. Now let's get inside that function. If you want to go to this function, just press and hold the left control key, then click on this. It takes you to the function GPIO init in the main.c itself. And as you can see in this function, HAL API, HAL GPIO init is used to initialize the selected GPIO pins, all these pins, which is used for controlling the LEDs like blue LED, green LED, and the red LED. Remember, these are the labels you provided while you selecting the pins. Now in this function, as you can see here, initially the output level was set to low, as you can see pin reset using the HAL GPIO API, that is HAL GPIO write pin. And then HAL GPIO init is used to initialize all these pins of the GPIO port A peripheral. And these are the configuration details what you provided using the pin configuration window. Now, if you are wondering from where these APIs are defined, these APIs are the hardware abstraction level APIs. So HAL signifies this API belongs to the hardware abstraction layer, which is actually added by this IDE whenever you generate the code. You need not to worry about that. And the second word GPIO signifies to which peripheral this API belongs to. Then this word signifies its purpose. Now, if you want to locate this API, of course, you can right click on this and go to open declaration here. But these APIs come from the hardware abstraction layer, which you can locate in the drivers folder here. Go to the drivers and go to the HAL driver here. Here, go to the source, and here you see the GPIO driver file. That means a driver file which governs the GPIO peripheral. Here, you just press Control key plus O. When you do that, it opens up all the exposed APIs from this driver file. So wherever you see the keyword HAL, that means those are exposed APIs. That means you can call those APIs from your application. And here it is, the write pin API is right here. And the init API is right here. In the next exercise, let's say if you are using ADC, then you have to use HAL underscore ADC like that. This is a driver file that is HAL GPIO.c, and this is automatically added by the code generation engine of this IDE whenever you select a particular peripheral or whenever you enable a peripheral in the IOC file of this project. Apart from that, in the core source folder, you also have HAL MSP.c. This is currently almost empty. So here this file is also auto generated. I mean, the IDE will keep the peripheral initialization code here. Currently there is no peripheral initialization codes. So later when we use some other peripherals, then you will see that the code generation engine also puts some initialization code here. After that, there is it.c. Here, this file contains all the interrupt handlers and exception handlers of your microcontroller. Currently, we are not using any peripheral interrupts. Whenever you enable peripheral interrupts, those interrupt handlers will be automatically generated and it will be stored in this particular file. So currently you see some default exception handlers of the processor, that is ARM Cortex-M. Currently these are some dummy handlers. They are not doing anything useful, so they are just trapping in an infinite loop, something like this. Okay, so now what we'll do is we will compile this code. We will generate the hex file or the binary file or the ELF file, and we will execute this program on the target board to see toggling LEDs. Now let's add the code in the main.c file under the main function to toggle the LEDs, which is the objective of our project. And the LEDs must be toggling continuously. That's why add the code in the while one loop of the main function in the main.c file. Remember that whenever you are adding code to the file which is auto-generated by the Cube IDE, then you have to be careful. So you must put your code after this tag called user code begin, and you must not put any code after this tag, that is user code end. Otherwise what happens is, let's say if I put some code here, so let's say I call some function here, let's say LED toggle. If I put any custom code after the tag end, then when you next time regenerate the code, so the code generation engine of this IDE will overwrite this file and it will remove the custom code what you have added. That's why care must be taken to add your custom code. So always keep the code between user code begin and user code end tags. So we will put the code after this tag user code begin in the while loop. So we have to toggle the LEDs, right? For that you have to use the HAL GPIO API provided by the GPIO driver file. That's why just type HAL and the peripheral name, that is GPIO, and then press and hold the left control key, then press the space key. It will give you suggestions of all the exposed APIs from the driver file, that is GPIO.c. Basically it is listing all the exposed functions which start with the name HAL_GPIO. So here, as you can see, we have an API called toggle pin. So let's just select that. And for this API, you have to supply two arguments. The first argument is the GPIO port, and the second argument is the GPIO pin. GPIO port, we know what is the port, that is GPIO A, because our all LED pins are connected to the GPIO port A, as you can see in the schematic here. All these GPIO pins are connected to the GPIO port A. After that, pin. Here, the pin, so let's toggle the first LED, that is this one. So GPIO pin 1 and GPIO pin 2, GPIO pin 3. You can use this macro GPIO underscore and hold control plus space key. As you can see here, GPIO, just type pin 1. You can select GPIO 1 here, like this. Otherwise, you can go to main.h. In the main.h, the code generation engine of this IDE is already generated some labels, as you can see here. User LED blue pin, it is actually hash defined that to GPIO pin 1. The code generator is generated these macros by taking your labels, what you had provided for the GPIO pins in the IOC file of this project. So you can use these labels instead, which actually gives more clarity to your code. Let's use these macros. Anyway, it is there in the main.h, and main.c includes that main.h here. Instead of writing like this directly, which doesn't reveal its purpose, so I'll just use user LED blue pin. I have to toggle 3 LEDs. I'll just call these functions 3 times, and in the second case I'll select green pin, and here I'll select red pin. And for this port also, you can select user LED blue port instead of GPIO port A, because anyway, as you can see here, it is hash defined to GPIO A. Basically, this gives more clarity in your code. Here, user LED green GPIO port and user LED red GPIO port. So once the LEDs are toggled, then we will add 1 second delay. For that, you can use the API called HAL underscore delay. So delay, just call this delay. If you want to explore this function, you can go to that function, which is defined in the HAL.c, and the delay is the input parameter, and it must be in milliseconds. As you can see here, the value must be in milliseconds. So this is basically a blocking delay. As you can see, it uses the while loop here. It's a blocking delay. So we will say 1000 milliseconds. That means 1 second. First, the LED is toggled, then it waits for 1 second, and then it repeats. Let's test this project on the target board. But before that, we have to compile this project and generate some binaries. First, let's compile this project. So you can go to the project and select that. Here, right click and go to build project, which compiles your project. Let's do that. Let's click the build. And as you can see, the build is started in this window. As you can see, this IDE is invoking a cross compiler called ARM none EABI GCC. So this is actually a compiler which runs on host machine, like in this case Windows machine, and generates the code for the ARM Cortex M microcontroller or processor. As you can see, it compiled our project, and as you can see here, let me just close this for a time being, build analyzer and these other tools currently not required. As you can see that the software has generated the final executable file in the format .elf or .elf. So this is the final executable which you can load into the target microcontroller and you can run your program. And this file is also helpful if you want to debug the project using debuggers. So if you don't have any plan to debug the code, but just to run the code on the microcontroller, then you can also generate other formats of the output file, like the .bin file or .hex file. Suppose if I go to the project settings of this project, let's go to the settings of this project. Just right click on go to the properties and go to the build, go to the settings, and here go to the post build outputs. You can select these options so that the IDE can also generate the output file in the form of .hex and .binary along with .elf. Let's apply and close this, and let me just clean this project. which will delete all intermediary object files and other files created during the previous build. So it will delete all those files, and let's again build the project. As you can see, it has created the .elf file, which is actually an executable, and along with that it also generated a pure binary file and also a hex file. Now let's see the difference between these different output file formats. The first one is .elf, which stands for executable and linkable format. So you have to use ELF format if your goal is to flash the code onto the target hardware and also debug the code using debuggers. Because the ELF format contains not only code and data of your program, it also contains a lot of metadata. That means other information like symbols information, which will help the debugger or the IDE to debug the code which is running on the target. That's the purpose of .elf. Along with code and data, it also contains detailed metadata, which incorporates debugging information and symbol tables. And there is another output file format, that is .bin, the binary file. It is actually a pure raw binary image of your compiled program, which just contains code and data, that's it. And it doesn't contain any metadata. It doesn't contain address information, etc. So a very raw format of your program is .bin format. And we will use this bin format if we have a simple bootloaders to program the microcontroller, as in this case. So in this case, we are using a Fastbit STM32 Nano board, which can be programmed using simple inbuilt bootloaders. We can use this format, just a .bin file we can use. So if you have simple bootloaders, then if you want to program the device directly, then you can use the .bin format. And there is another format called Intel hex format, or .hex or .ix. This is ASCII text file format representing binary data along with address information and data integrity checksums. Since this file includes a checksum, which can be used to verify the integrity of the data as it's programmed into memory. If you want a data checksum feature, then you can use Intel hex format. So I would suggest you to explore more on these formats by doing some research. Now let me just explain about this Fastbit STM32 Nano board. It's a very compact design. First of all, the main microcontroller is actually at the back side. This is a main microcontroller, which is STM32F303 family of microcontroller from ST. After that, this is a USB mini connector from which you can supply USB power to the board. It also supports the USB data communication. So this is the connector where you can connect the external debugger like SWD based debugger to debug the code which is running on this board. And these are some connectors to connect LCD or any other components like sensors. After that, it also has onboard MPU 6050 accelerometer and gyroscope sensor, and it also has a virtual COM support. And apart from that, here you can see 3 buttons. First of all, this is a user button which you can use for some of your applications. That's a user button. And this is a boot button. By using this boot button, you can put the board into boot mode so that you can download executable binary into this board. And we are going to use this in our project. And this is a reset button to reset the microcontroller. And it has a couple of LEDs. One LED is at this side and another LED is at this side, and there is one LED here as well. So 3 onboard LEDs which you can use for your projects. Now let's see first how to connect this board to the computer. You just have to take one USB cable which comes with this board, that is the USB mini cable. Just connect over here like this and connect this end to your laptop or computer USB port. I just connected the board, and here there is one LED is already glowing because some program is already running on this microcontroller. Here, as you can see, when you connect the USB to give power, there is a power indicator. So this is a power indicator LED. That is a red LED that must glow. That's it. So this is how you connect the board. After you connect the board to the computer, so the computer will detect this board as a virtual COM port that you can see in the device manager of your host machine. Go to the device manager. Here, just go to ports, and here you will see USB serial CH340 virtual COM port enumerated in the host machine. So this number could be different. This is because this board has onboard CH340 USB to UART converter. So you must see this port enumerated on your host machine. Now let's flash this program onto the target hardware. You just connect the board to the computer. After that, open the STM32 CubeProgrammer what we had installed in the previous video. Let's launch STM32 CubeProgrammer, which is right here. After that, here in the STM32 CubeProgrammer, select UART because we are downloading the binary file of our program using the UART protocol. Just select UART, and you may keep this default settings of the UART, so don't change anything. Then cross-verify to which virtual COM port the Nano board is being connected. So as I explained, when you connect the Nano board, it will be enumerated as virtual COM port, and currently my computer is showing that it is connected to COM3. This you can verify by opening the device manager application in your host PC. It is currently showing as COM3. After that, click on Open File. You need to go to your project directory, which is very easy to locate. You just go to your project and click on the properties here. Go to the resource. Here you can see the location. This is the location of project. Let me open that in the File Explorer. This is a project, and if you get inside that project, you will see a folder called Debug. Get inside that, and here you will see all the different output files which have been created, like elf, hex, and bin. Now let me open the CubeProgrammer, and let me give that path to my project. So this is a path to my project where the bin file is located. I have to give that in the CubeProgrammer. So let me just paste that path here and click open and select the bin file. So the bin file is open. Now you have to click connect. But before connect, you have to do one thing. That is, you have to keep the board into boot mode. Now let's see how to put the Nano board into boot mode, which is very simple. Here is a boot pin. You just have to press and hold the boot pin and then apply reset like that and release the boot button. Now it is in the boot mode. So once it is in boot mode, you can go to the STM32 CubeProgrammer and press connect here. I just clicked connect, and as you can see, it is connected. Then you can click on download, which downloads this binary file into the board. Let's click that. It says download is complete. And then you just press the reset button. Now as you can see, our program is running on the Nano board. Basically, the program was about toggling all the user LEDs. Since we pressed the reset, so the board is now exited from the boot mode. As you can see in the CubeProgrammer, it is saying that the connection to the device is lost, so that is normal. And if I try to connect to the board, it won't be successful because the board is not in the boot mode. If you want to program again, or if you want to download the executable again, then you have to again keep this board into boot mode. That we can do simply by press and holding the boot button and then applying the reset. As you can see, now the board is went into the boot mode, and now again you can program the board using the STM32 programmer. So this is how you program this board without using any external debugger. Now, since any debugger is not connected to this board, you cannot debug this code. In the next lecture, we'll see how to download a code to this board using a debugger, and we'll try to debug the code which is running on this board. For that, STM32 programmer is not required. You can do it on the STM32 Cube IDE itself. So you just saw how to program the target board using the STM32 Cube programmer without using any debugger connected to the board. So we just transferred the executable file from host machine to the target using the bootloader present inside the board. The board actually has a STM32 microcontroller which has got inbuilt bootloader. With the help of that, we just transferred or flashed the image from host machine to the target machine. Now in this video, we will understand how to flash the code onto the target hardware using an external debugger connected to the board. There are many SWD protocol based debuggers are available in the market. On the board, you get the SWD pinouts to which you can connect any SWD based debuggers so that you can debug the board. Now let's see how to program and debug the Nano board using ST-Link V2 programmer and debugger. This is a very low cost ST-Link V2 device which comes with this board. So this also supplies power to the board, so you need not to connect any USB here. We just connect this debugger to the board starting from the pin number 1. Let me just connect that like this, and these two pins are not used actually. Then you just connect this to the laptop. I just connected the board to the computer via the ST-Link V2 debugger. Now you can go to the project and just right click on debug as and select this option STM32 C++ application. Here go to the debugger section and make sure that ST-Link is selected here. After that, interface is SWD, and this is Cortex M4, and after that all these options you can leave as default, and frequency. So the frequency is auto, or you can type in the processor clock which was 8 megahertz. That you have to type in terms of kilohertz, that is 8000, or let's keep this auto. Then apply and OK. Now the IDE is going into the debug mode. So it will flash the code, that is blinker.elf, onto the target, and it goes into the debug mode. As you can see, it is asking you to switch the perspective to debug perspective. Let's click switch. Now as you can see, the breakpoint is hit to the first function call of the main function. So the code is not running now, it is actually halted at the very first instruction of the main function. This clearly indicates that the board is in debug mode and the code is not running, because as you can see on the board there is no activity of the LEDs. Now you can run the code in one go using this button resume. So if I click this, as you can see, the code will start running. If I want to halt the code execution, I can press this pause button, that is suspend. Let's click that. Now as you can see, the code is again halted. And if you want to continue, then you can press the resume here. Or if you want to start all over again, you can reset the board from here itself, from the IDE itself, without pressing the reset button on the board. That you can do using this option, reset option. As you can see, this is a reset option. So just click that. As you can see, the board is resetted and the application starts all over again. Now let's set one breakpoint. So let's keep the breakpoint at this line. That you can do by double clicking on this blue strip in front of that line. Just double click so that you can enter a breakpoint. I just entered the breakpoint here, and then let me hit run or resume. As you can see, the code ran up to this point and it halted at this line. And now let's put another breakpoint here at this line. I just inserted another breakpoint, and let's hit resume again. And as you can see, this line is executed. That means it actually turned on the blue LED, as you can see on the video here. So you can also do step-by-step execution by using this step into, step over functionalities. If I use this step over button, let me click that. As you can see, the code has progressed by one step. As you can see here, green LED is also on. After that, let me press the step over again, and this time it will execute this line, that is the red LED. As you can see, the red LED is also on. That's how you debug the code. And when you are in debug mode, you can also check all the special function registers of the microcontroller or the processor registers by going into the Windows section, go to Show View, and go to SFRs. Here you can observe all the microcontroller specific peripherals registers. Like in this case, I'm using GPIO port A. So I can go to the GPIO port A and go to all these registers, and I can observe the activities happening. Especially in this case, you just check ODR register because that register controls the output state of the GPIO pin. In later videos, we'll also use some other peripherals of this microcontroller. And in this section, Cortex M4, you can observe the control registers of the processor. You can observe the NVIC registers and other registers. And in the show view, you will also find a disassembly of the code. That means the assembly code generated for the C code. You can even debug the code instruction by instruction. For that, you have to enable this option, that is instruction stepping mode. If I activate that, now it is activated. After activating that, if I do step into, you see here, the code is actually executed instruction by instruction, not function by function. Instruction by instruction. So if this is not enabled, then the step into or step over, it will not debug your program instruction by instruction. It would be rather statement by statement debugging. I think that is another nice feature which is available in this IDE. After that, you can check the processor registers here in the registers tab, and there are so many other features we will explore as we make a progress in this course. Now we are in the debug perspective. Now if you want to go to the C or C++ perspective where you edit the code, you can click on this icon. Sorry, not this one, this one. C++ icon is there. Just click on that. So that will take you to the editing mode where you can edit code. Suppose, let's say I want to change this program. Let's say I want to change this to 500. I just edited the code. Now I want to rebuild this program and then again reflash this code onto the target. But the IDE is already in the debug mode. You need not to terminate the debug mode. What you do is you come to the C and C++ mode. So do your editing of the code, then go to the debug mode, okay, debug perspective by clicking over this icon. Now I came into the debug perspective. Here what you do is you use this option, terminate and relaunch. So it will end the current debug session, but it will compile the source code again and it will relaunch everything in one button. Let me just click that. As you can see, it is again compiling your code because you have edited the code, and then it is connecting to the debugger and it is flashing the newly generated executable. Just click on switch here. Now as you can see, it again entered the debug session, and let me hit resume here to run the code. Now as you can see here, there is one breakpoint set. Let me remove these breakpoints. Just double click on that dots. It will remove the breakpoints. Or if you want to kill all the breakpoints, then you can go to breakpoints tab here. It is right here, breakpoints. Or you can go to the show view and breakpoints here, and you can use these options to remove all breakpoints. Now let's hit resume because the code has halted here. Hit resume, and now as you can see that the LEDs are toggling with the duration of 500 milliseconds. I hope you get some idea about debugging the code which is running on the target. Now if you want to terminate this debug session, then you have to use this option, that is terminate. This will terminate the current debugging session and it will go back to the C and C++ perspective of the IDE. Let's click this. As you can see, it has come to the C perspective where you can again continue with your project. Now let's see the first case using timer interrupts with a delay of 500 milliseconds to toggle the onboard LEDs of the board. Basically, you have to configure the timer to generate interrupts for every 500 milliseconds. These red lines indicate timer interrupts. And whenever a timer interrupt is triggered, it will run the associated interrupt service routine. There we will toggle the LED. So interrupt service routine is nothing but a simple C function which will get invoked or executed only when the associated interrupt triggers. In this case, a timer interrupt. And inside the ISR, you can take certain actions like toggling LED. In this exercise, we will understand how to configure the timer peripheral to generate interrupt for every 500 milliseconds. So that is what we call as using timer for time-based generation. We'll learn using timer for time-based generation. You can use STM32's timer for various other tasks, but in this exercise, we will understand time-based generation. And you will also understand in this lecture how to generate the ISR function and how to edit it. Now let's go back to our IDE and let's do this. Now let's create another project. I'll go to File, New, and this time I'm going to select, since this is a little modified version of the first project, I'm not going to create entirely new project. What I'm going to do is I'm going to select this option, STM32 project, from an existing IOC file. Let's select that because I need the IOC file of the previous project for this exercise. So where we just configured the onboard LEDs, otherwise I have to do all over again. Here it is asking me to provide the IOC file. I have to take from this project. So I'll just click browse and I will head over to my earlier project folder. Here I will select this, open. So here we will change the name to interrupt. After that, targeted language C, everything is same. Just click next here and finish. As you can see, our new IOC file is already configured with all these pins and selecting the earlier microcontroller. So we did not have to do selecting pins and microcontroller all over again. Now in the IOC file, just open the IOC file if it is not opened and go to the timer section. Here there are many timers. So we will select one timer. Let's say I select timer 6 and its mode is not activated. Let's activate it. Here it is. And now it is giving you some options to configure these things. Now we have to configure these parameters of the timer 6 peripheral in order to achieve the desired time-based generation. Now, before configuring these items, first let's understand few things about the timer 6 peripheral. Now let's check the block diagram of this timer 6 peripheral. This image I actually took from the reference manual of the microcontroller. And if you are using some other microcontroller of ST, then also you should refer to the same peripheral, that is timer 6, which is known as a basic timer. Now this is the block diagram of this timer, and as you can see here, there are a couple of things we must understand before using this peripheral correctly. First of all, you see here there is a section called counter. So it is like a main counting space inside the peripheral where counting happens. And that counting happens for each clock pulse of this clock, that is called as count clock. This is called as a count clock. The reason is, using this clock, the counter counts. So if you are wondering whether it up counts or down counts, so timer 6 peripheral is always up counting counter, always up counts for every clock pulse received here. And auto reload register, ARR, is a user programmable register where you have to feed some value. And when this counter up counts and reaches this value, then an interrupt will be generated. That's what we call as update event. There is prescaler, so this is also called as clock divider. And by configuring this, you can control this clock by dividing this clock. And if you are wondering what is this clock is a main clock which comes from the RCC block of the microcontroller, that is reset and clock control unit of microcontroller. So basically you can treat this as a main clock, and that main clock can be divided using prescaler to control or to slow down the counting clock. Now let's understand how the time-based generation works. First, what you have to do is you have to load some value, that what we call as period value, into the ARR register. That will set this mark, some value. So we will practically see how to calculate this value. Then the counter always starts from 0. So you have to activate the counter or the timer. And for every clock pulse of the count clock, the counter up counts by 1, like this. And when it reaches the value which is stored in the ARR register, that's the end actually. It rolls back to the 0 and it issues an interrupt. So that's what we call as update event. And it starts all over again. Like this, it starts from 0, up counts, reaches the ARR value, triggers the update event and rolls back to 0 again, and it starts all over again. Like that, it works and you get continuous interrupt on every update event. So the auto reload register, ARR, it is one of the important register when we deal with the basic timers. So this is a user programmable register which holds the value that the timer's counter will count up to. When the counter reaches the value specified in the ARR, several things can happen based on the configuration. So the timer can issue an interrupt. The timer can trigger an interrupt when it reaches the ARR value. This interrupt can be used in your application to execute a block of code, such as updating variables, toggling GPIOs, or any other task. And whenever the counter's value reaches the ARR value, the counter resets. The counter automatically resets to 0 or a specified preload value after matching the ARR. That is very important, thus starting the fresh counting cycle. As you can see in the chart, so just see the G underscore counter variable here. This is a pattern of the timer's counter running up to the ARR value. So this is the 20,000 is the ARR value, and this is a counter running. It just increments from 0 and it goes all the way up to the ARR value 20,000, and when it reaches the ARR value, it resets back to 0 and another cycle starts like that. This is the behavior of the basic counter of the timer. Now the question is, how do we calculate this ARR value? Now that depends on how much time base you require for your application. So for this application, we need a time base of 500 milliseconds. That 500 milliseconds time period must be converted into a suitable number. That's what we call as ARR value, so that you can program or put that number in the ARR register. Let's see how to convert the time-based value like 500 milliseconds to an ARR value, that is auto reload register value. Here is a formula to convert the desired time base in seconds into ARR value. First, you have to calculate what is the count clock frequency of the timer. That is denoted by clock_count. So this is the clock pulse using which the counter upcounts, and that is derived by slowing down the main clock frequency applied to the timer. So the prescaler is used to slow down this clock. That's a divider. So the prescaler value is set to 0 by default in the STM32 microcontroller. So that means the divider is by default 1. That means by default clock count is equal to main clock frequency. So if you check the block diagram, this is a clock count and this is the main clock frequency, which is directly coming from the RCC block of the microcontroller. And this prescaler is by default 1. So this is equal to this clock. Now, what is the main clock frequency in our project? Let's find out. Now I'm in the project. So now let's find out what is the main clock frequency that is applied to the timer peripheral, that is timer 6. For that, go to the clock configuration. As you can see, this is the main system clock, our microcontroller, which is running at 8 MHz. And here is a timer clock, APB1 timer clock and APB2 timer clock. So APB stands for a bus, which is called as a peripheral bus, advanced peripheral bus. There are two buses in the microcontroller for the peripherals connections. One is APB1 and another one is APB2. APB stands for advanced peripheral bus. It's a bus where the peripherals are connected. And as you can see here, this 8 MHz, which is the main system clock of the microcontroller, denoted by H clock, is directly fed to these timer clocks. That means the timer will be getting 8 MHz as its main clock. Now, if you want to slow down that clock, you can use these prescalers here. So let's not touch these prescalers. Let's keep them as ones. So this main system clock is directly fed to the timer clocks. Hence, 8 MHz is the main timer clock frequency. That means 8 into 10 to the power 6 Hz. That means here ARR is equal to 8 into 10 to the power 6 into desired time base. So we need time base of 500 into 10 to the power minus 3, right, minus 1. That turns out to be, this is 40, 0, 0, another 3 zeros here, minus 1. Let's convert that into hex. Let's see what that turns out to be. So I have calculated here. This turns out to be this value, 0 cross 3D 08 FF. This is a 3-byte data, 3 byte, right? First byte, second byte, third byte. But the ARR register in timer 6 peripheral of the STM32 microcontroller is just 2 byte. It's a 2 byte register. That's why we cannot use a 3 byte value here. Here in the reference manual. Let me open the reference manual, basic timers, timer 6. As you can see, auto reload up counter is 16-bit. That's why, this register itself is 16-bit register, 16-bit up counting register. That's why it cannot go beyond that. That's why we cannot feed 3-byte data into this register. So somehow we have to keep that within maximum value for the 2-byte data. How do we do that? Now we'll do one thing. So we can do that by reducing this value. How do we reduce this value? We reduce this value by using this prescaler. Let's say I set the prescaler to 7. So 7 plus 1 becomes 8. 8 divided by 8. So this clock becomes 1 megahertz. Now let's recalculate ARR value. 1 megahertz, 1 into 10 to the power 6 multiplied by 500 into 10 to the power minus 3. That turns out to be 500,000. Now let's calculate. Minus 1. Now again, that turns out to be a number which is greater than 2 byte. Hence, we cannot use these values. Now let's try another configuration. So let's select this as 127. Prescaler as 127. And we know that this is 8 megahertz. This turns out to be 8 megahertz divided by 128. That turns out to be 62,500 hertz multiplied by 500 into 10 to the power minus 3. Let's do that. So into 500 divided by 1000 minus 1. Now we get a value which can fit inside a 2-byte register, that is 31,249. 31,249. Now we will use this value as the ARR value. So this is our ARR. Now let's go back to the IDE and let's go to the pinout configuration, timer 6. Here prescaler, that is 127. If you use 127, what the microcontroller does is it will add 1 to it and it will make it as 128. Then up counter mode is always up here, so you cannot change it. And period value is just put the value what you had calculated just now, 31,249. After that, in this section, trigger output parameters, select this option to update event, because whenever the counter overflows, we need an update event. So when that update event is generated in the timer peripheral, then we can get an interrupt out of that. If you understand more on this, you can study the timing diagram given in the reference manual. In the basic timers, just go to the timing diagram given here. Maybe you should refer this one here. As you can see here, there is a counter register which is counting, up counting 32, 33, 34, 35. And note that the ARR value is currently set at 36. When it becomes 36 and it matches with the ARR value, the counter resets. That means the counter has overflown. That's why the update event is generated in the timer. Update event is generated, which is going to set the update interrupt flag. Here it is. So the update event interrupt flag will be set. And if interrupt is enabled, then this is going to issue an interrupt. That we can do by going into the NVIC settings here. So go to the NVIC settings and make sure that timer 6 interrupt is enabled. Whenever the interrupt flag is set, interrupt will be issued. Now you may be having one question, that is, how do I set priority for this interrupt? There is no the priority sections. Priority sections are there. Here the priority columns are there, but they are not editable. As you can see, I think you can edit that using the system core section here. Go to the NVIC, and there you can edit the priority for the interrupts. Currently it is set at highest priority, so let it be. Maybe you will use sometime later in this course. Currently it is set to 0. You can choose any value here. And here this column also shows currently how many interrupts and how many processor exceptions are enabled. As you can see, all the processor exceptions are enabled here. As far as interrupts are concerned, only one interrupt is enabled, that is timer 6 interrupt. As you can see, these processor exceptions cannot be disabled, so they are always selected. Now let's go to the code generation, and as you can see, by using this section you can automatically generate the interrupt service routine code. As you can see in this column, generate IRQ handler. So all these are checked. That means the STM32 Cube IDE is going to generate the ISR functions for all these exceptions as well as selected interrupts or enabled interrupts. These are the settings you have to do. For first time it looks kind of tedious, but believe me, it is very simple. The first thing, let me just summarize for you. If you want to configure any peripheral, so just find that peripheral here in the pinout and configuration. Let's say I want timer 6, and I'll go there and I've set all the parameters for that, and in the NVIC settings I will enable that interrupt. Here I cannot control the priority settings and the IRQ handler generation. For that you have to go to the dedicated section given in the system code, that is NVIC, and if you go there it will show you the enabled interrupt for your peripheral, and also by using these columns you can control the generation of IRQ handler. Very simple. And here you can also configure the priorities. Now let's go to file and let's save, and now it is ready to generate the code. Let's click yes here. Now it is generating the code. So now the code generation is completed. Let's check. First of all, let's start from the main function. In the main function, as you can see, it was previously there. Now the code generator has added the timer 6 in it. In this timer 6 init, it has taken the values or the configuration values you have provided, like prescaler values and the period value, and using those values it actually initialized the timer 6 peripheral for the time-based generation using this HAL API call, as you can see here. That's about initializing the timer to generate a time-based interrupt for every 500 milliseconds. So that was our objective. That's about initializing the timer. As you can see, it doesn't run the timer, or it doesn't trigger or enable the timer. It just configures it. After that, let's go back to the main function again. And here, after this line, as you can see, the timer is actually not running. Remember that. So you have to run that by calling the timer specific API that I will explain in a moment. Now let's go to the it.c. In the it.c, as you can see here, it has added timer 6 IRQ handler. So this is the interrupt service routine or IRQ handler of the timer 6 peripheral. A timer 6 peripheral or a timer can generate interrupts for various reasons. And one of the reasons could be because of overflowing of counter, that is when an update event happens inside the timer, and that is the case we are dealing with. And here you can see that the code generator of the STM32 Cube IDE has added this particular function call, which actually comes from the HAL layer. This function handles, which is defined in the timer driver file, handles the interrupt. What this function does is it finds out what exactly is the reason for the timer interrupt, and it handles that reason. Basically what it does is it clears the interrupt flags related to that particular event. Let's get inside this function. And let's see what exactly it is doing. As you can see, this function is defined in the HAL layer. The exact file name is hal_tim.c. And this function handles timer interrupts. As I said, a timer interrupt can be generated because of various events like capture compare events, output compare event. It could be because of an update event. That is our case. If you just browse through this function, you will see a section called timer update event. We are actually interested in this portion of the code. As you can see, it first confirms that this interrupt happened because of timer update event. As you can see, this code here clears the timer update flag. So this flag must be cleared, otherwise you will get spurious interrupts. If you are wondering where exactly all these things are mentioned, as you can see in the reference manual, if you go to the timer 6 registers and if you go to the status register, as you can see here, there is one flag called UIF that stands for update interrupt flag. Whenever update event happens in the timer peripheral, so this flag will be set. And whenever this flag is set and interrupt is enabled for this particular flag, then interrupt will be issued. Basically, this is set by the hardware on update event and it must be cleared by the software. And that is exactly the timer interrupt handler code is doing. That means it is absolutely necessary to call the peripheral IRQ handler function given by the HAL inside the IRQ handler. And if you again check this function, let's again go back to the timer update event flag handling section here. As you can see, it clears the update event flag. Then it calls period elapsed callback. That means it calls the user implemented callback. So that means in your application like main.c, you just have to implement period elapsed callback function. And the interrupt handler will call that function whenever update event happens. Now, if you are wondering what exactly is the name of the period elapsed callback so that you can implement that in your main.c file, that name is actually fixed and it is given in this driver file. So in this driver file, just type control plus O, and it will list out all the APIs and other symbols of this driver file. Here you just search for HAL timer period elapsed callback. Here it is. So the period elapsed callback is an empty function with weak linkage. You have to implement this function in your application like main.c without this weak attribute. Here, the weak is actually the GCC attribute, which helps you to declare the same function somewhere else in the program without this attribute. In that case, the linker will prefer the non-weak declaration over the weak one. So if this function is not defined anywhere else, then the linker will consider this function. But if you define the same function somewhere else in the program without this weak attribute, then the linker will neglect this function, but it will consider the non-weak definition of the same function. That's a beautiful attribute. You can make use of that. That's why you can just copy this and go to your main.c file. You can define that function here. For a time being, I will define that function here. Let's say under this tag, user code begin and user code end. So you have to put the code, the user code, you have to put your own code between these begin and end tags. Remember, otherwise next time when you do code generation, then the code generator may overwrite or remove the code what you have written. Here, just remove this function. And then you can remove all these things. If you don't use this variable, then you can keep this. So I'll just remove this. Here we will toggle the LED. Now let me just summarize what and all happened here. First of all, you have your microcontroller and there is a timer 6 peripheral, and first what happens is update event happens inside the timer 6 peripheral whenever the counter overflows. Then the UIF flag is set in the timer 6 peripheral. Since interrupt is enabled, the timer peripheral will issue an interrupt to the processor. Here NVIC is one of the block of the processor which controls interrupt, so it stands for nested vector interrupt controller. And when the interrupt is issued to the processor will immediately call the IRQ handler, the timer 6 IRQ handler, which is defined in the it.c. And you should immediately call the HAL given function to handle that timer interrupt. So this function will identify the reason for timer interrupt, clears the appropriate flag, in this case UIF flag, because it's an update event. Then it calls user implemented callback, in this case period elapsed callback. And that callback's name is fixed and you have to implement that in your main.c function without this weak attribute. And there you can keep your code, in this case like toggling an LED. So we were discussing about the period elapsed callback in the previous video, and here we must toggle the LEDs. Let's go back to our earlier project. Here main.c, in the main.c we wrote all these LED toggling code in the main function. Let's copy this code and let's go back to the current project, and here I'm going to place that code. For every 500 milliseconds, the timer elapsed callback will be called and our LED will toggle. Let me just save this and let me just first compile this project. Now let me also connect my hardware. The hardware is connected. Now let's debug the project. So I have connected my hardware through the ST-Link debugger, so I can debug my project. Let me just do that. This is a new project, so every time you try to debug a particular project, a new project, it will always pop up this window. Here you must just see whether all these debugger connections are fine or not. As I explained in the first project, it must be SWD, Auto, Cortex M4. Everything is fine. I'm going to apply. Okay. First of all, the code is not running. It has halted in the first instruction of the main function. So I'm going to first keep a breakpoint in the period elapsed callback here. So I just placed a breakpoint here. If everything is fine, then the timer must issue an interrupt and the interrupt handler must call this period elapsed callback for every 500 milliseconds. Now let me run this code. As you can see, I am not getting the proper output here. Of course, my code is not working. The LEDs are not toggling. That's because this period elapsed callback is not hit. Now, the reason for that is it is very trivial. We did one mistake. We just initialized the timer. We did not start the timer. We did not kickstart that counter, up counter, which is there inside the timer. That was our mistake. No problem. So we will go here and we will just use this API call HAL timer underscore. As you can see here, there is a function called base start IT. So just use that because we are using interrupt based time based generation. That's why you have to use time base start underscore IT. Then you just supply the timer handle, that is the timer handle you can get here. In the main.c, as you can see, there is a global variable called htimer6 that is called as timer handles. Basically, it's an instance of the timer handle structure. So this variable will have all the information about the timer 6 peripheral what you are using in this application. So whenever you want to deal with the timer 6 peripheral here, you must use this handle. So we have to send address of this variable. So you have to send the address of this timer handle variable. That's all you need to do. And let's save, and we have to recompile and reflash the code. That we can do in just one click by using this option, terminate and relaunch. Let me click that. Now as you can see, the code is flashed successfully, and let me hit run or resume. As you can see, now the breakpoint is being hit here. So we are indeed coming into the period elapsed callback. Now let me just remove this and let me just hit resume here. And as you can see, it again came to the period elapsed callback. So this callback will be called for every 500 milliseconds. In the left hand side, you can see the call stack. First interrupt will be triggered, so IRQ handler is executed, and then the interrupt is handled in this function, and this function calls the period elapsed callback. Let me remove this breakpoint and let me hit resume, and now I can see that all the LEDs are toggling with some period. But how do we make sure that the period, the time-based generation, is really for 500 milliseconds? How do we verify that? We can verify that by connecting some logic analyzers to the GPIO pins which are driving the LEDs. Now in this lecture, let's trace the GPIO signals using USB logic analyzer. So USB logic analyzer is a very handy and low cost device by using which you can trace the microcontroller pins activities. It will be very helpful for us when we deal with more complex projects, like projects involving serial communications or parallel communications. So this device will be very helpful to trace the pins activities or trace and decode the packets of the serial communication interfaces such as SPI or I2C or CAN, etc. Now, in this example, we will use this USB logic analyzer hardware to trace the activities of the onboard LEDs which are connected to the GPIO pins of the microcontroller. So for this, you need to have this USB logic analyzer hardware. There are many different logic analyzer hardware are available in the market. You just buy as per your budget. And this USB logic analyzer comes with a USB cable. You have to connect this USB end to the computer so that computer can collect the samples which are coming out of this USB logic analyzer. And this USB logic analyzer has 8 channels, as you can see here. The pins is not visible from this picture, but there are pins. Totally 8 pins are there. That means at a time you can capture activities of 8 microcontroller pins. And there is ground and clock pins. Here in this example, we are going to take the first channel CH1 and you connect that to this P1 header. So this is the P1 header of the nano board, and you connect that to third pin of the P1 header. This is the first pin, second pin, and the third pin, which is actually LED 1. The exact microcontroller pin is PA1. So by using this channel, we can trace the activity of the GPIO pin PA1, which is connected to the LED 1. And ground connection is very important. So connect ground pin of this logic analyzer to ground pin on the board. So the ground point you can get in header connector PA1's 10th pin. So once you do this connection and make sure that the code is running on the target board, it must be powered and code must be running, that we can capture the LED activities. Now you need to install USB logic analyzer software, and we'll be using Sigrok's PulseView software in this video. So this is an open source visualizer, and you can visualize the activity of the microcontroller pins. So to download this software, you visit this website of Sigrok, and I am right here in the download page. You just download as per your machine. Mine is Windows, and I'll be downloading PulseView 64-bit. So once you install that software, just launch the PulseView. As you can see here, it just shows demo device. Basically, the no device is connected to my computer right now. So let me connect the USB logic analyzer hardware to my computer. I'm connecting that. Let's see whether it detects or not, whether the software detects or not. I just connected the USB logic analyzer hardware to my laptop, and as you can see, it is still showing demo device. What I can do now is I'll just click on this demo device, and it is asking me to choose the driver. So you just select FX2 ALA firmware generic driver, and once I do that and just click on this scan for devices, and it will show you this device name. That means this software is detected my hardware, but this may not be the case for you because you may not see anything here. So if you don't see anything here, then that means the driver for that device is missing on your computer. So what you do is you just cancel this and close the software. Then you go to the search bar and type PulseView Zadig PulseView. Just launch this application. Once this window opens, here you may see unknown device. Since I have already installed the driver, it is not showing me anything here. Basically, I can here go to list all devices, and then if I select this one, so it actually now showing me the device which is connected. So the details of the USB logic analyzer hardware which is connected to my PC. Since I already installed the driver, so the option is reinstall driver. For you, it may be unknown device here. Don't worry at all if you don't see these options. For you, it may be unknown device, and there could be some USB vendor ID and product ID. Just click on install driver. Let me just click reinstall driver in my case. Now it is installing the driver. Please wait until it says driver installed successfully. Let me close this, and let me close this as well. Let me relaunch my PulseView software, and now as you can see, it is showing the exact logic analyzer hardware name. So it could be different for you. Now you can click on that. So here you can select generic driver for FX2 based LS, and if you just click the scan for devices, it will show you the device. So if you don't see this even after installing the driver, so please disconnect and reconnect the USB logic analyzer hardware, or you try reinstalling the driver using Zadig PulseView application. Now the software is connected to the USB logic analyzer hardware, and now let me make these connections so that I can trace the GPIOs. Now I just connected the USB logic analyzer's channel to the onboard LED pin, and now let me just click on session 1. So if you don't see any sessions, you can just click on this. Now it is saying again no device, so let me select the device, which is this one. Then let's configure the number of samples. So I'll just keep this for 1 million samples, and the sampling rate for a time being you can keep 20 kilohertz, no problem for this application. And then click on run. Now as you can see, I am seeing the GPIO activity on channel 1. The software is saying D0. Let's stop this. This is how the LED is toggling. We are making it high and low. And now we configured in our software that the LED must toggle for every 500 milliseconds. Now let's make sure that our timer is indeed issuing interrupts for every 500 milliseconds. That we can measure by using this cursors. Let's take the cursors, and let me just keep one cursor here and another cursor here. As you can see now, the time gap between these two cursors is around 500 milliseconds, almost equal to 500 milliseconds. So there is some error factor. It is not showing exactly 500 milliseconds. You can even try with, let's see. It's showing approximately 500 milliseconds. There's an error of around 0.25 milliseconds. That's okay. It could be a error factor introduced by the way we collect the samples and maybe because of the software. So we just confirmed using the logic analyzer hardware that our LEDs are indeed toggling at the rate of 500 milliseconds. The logic analyzer hardware is really handy and very helpful in tracing signals of your development board or any of your printed circuit board when you are doing projects. And in the next exercises, we'll also use this hardware to capture the serial communication protocol, and we'll also use the USB logic analyzer software to decode those serial communication data packets to understand how the devices are communicating with each other. It's a very helpful debugging tool which you must consider using in your embedded application development work. We were doing some variation of project 1, and we did this using timer interrupt. We just toggled the LEDs. Now let's go to the second part of this application. Using button interrupt, let's toggle the LEDs. So we'll do this in the same project. You have to toggle the state of the LED each time a button is pressed. Basically, what you need to do is configure the button which is there on the Nano board as an external interrupt source and use the ISR for the button interrupt to toggle the LED. Let's see how we can do this. Now, if you check the Nano board, there are 3 buttons actually. This is a user button, and there are 2 other buttons. This is a boot button, and this you use if you want to keep the board into boot mode. And there is a reset, hardware reset button. So we'll be using the user button, and this is a schematic of that user button. As you can see, the user button is connected to the microcontroller on the GPIO port A, pin number 0, PA0. So if you are using some other board, find out how the user button, on which pin the user button of your board is connected. And as you can see, when the button is open, which is by default, the PA0, the pin is driven to ground. That means the pin will be 0 volt. When you press the button, this switch will be closed, and this point is driven to high, that is 3 volt. But in this application, we need an interrupt, right? We want to have an interrupt. That means, let's say, whenever the rising edge is detected, because it is 0 volt, and when you press it becomes 3 volt, that means that causes a rising edge, 0 volt to 3 volt. So we should configure our code in such a way that we receive an interrupt at this point during rising edge. You can even consider falling edge if you want. Like when you release the button, it comes from 3 volt to 0 volt. That is falling edge. You can even configure the microcontroller to issue an interrupt during falling edge on the button. Let's see how to do all these things using STM32 Cube IDE. So I'm going to my project, the same project 001 LED blinker interrupt. Let's open the IOC file. Here now we want to take care of PA0. That is where the button is connected. PA0 is right here. Let's select that. And you have to configure this into GPIO external interrupt. EXTI means external interrupt. You have to select this mode. Let me do that. Let me select that mode right here. Now, as usual, you can configure more parameters for this GPIO pin by going into system core and go to GPIO. Here you will get the list of all selected GPIO pins in the pinout diagram. See here, there is an entry made PA0, and let's configure more parameters using this window. Now, as you can see, it is saying external interrupt mode with rising edge trigger detection. What if I want to configure this in falling edge? So you can even change this trigger detection. Just browse through this. Here it is, very tiny window. Let me just pull this. See here, you can change it to external interrupt mode with falling edge or both rising edge and falling edge. So you can even configure this into external event mode. Let's not worry about events. Let's just concentrate on interrupt. I'm selecting this. After that, you can keep this option, no pull up and pull down. User label you can give something like user button. After that, there are other parameters like this one, maximum output speed, that is not applicable. Let's leave this at this stage. We just configured the GPIO mode. GPIO has several modes like input, output, and interrupt mode. For this application, we configured that GPIO pin in interrupt mode. So we did not enable any interrupts or we did not do any interrupt configuration. We just changed the mode of the GPIO pin. Then let's go to NVIC here. And you have to enable interrupt for that particular GPIO pin. So let's do that enabled. Now, if you do interrupt related settings like setting up the priority, generating the interrupt service routine code, etc., you cannot do that here. That is interrupt specific. You just enable the peripheral interrupt here. That you have to do in a dedicated section called NVIC, that is interrupt controller. Here, as you can see, when I go there, it has got two options, NVIC and code generation. Here, as you can see, EXTI line 0 interrupt is enabled. And here you can set up the priority and everything. Now, there are two interrupts in this application. One is a timer interrupt and another one is EXTI line 0 interrupt, which triggers whenever rising edge is detected on the GPIO pin. You can set up a different priority for this interrupt, but let's not get into priority discussion for a time being. Let's keep this 0 as well. That means both the interrupts are of highest priorities. And then go to code generation. As you can see here, if you just browse here, so the generate IRQ handler option is selected. That means the code generator will create the ISR. So there is nothing much. Now let's save this and let's generate the code. Now the code generation is over and we must be able to see the GPIO interrupt handler in the it.c file. Just go to core, source and open it.c file. As you can see here, we got this function. So that is the EXTI 0 IRQ handler, that is external interrupt 0 IRQ handler. And that interrupt is again handled in this function. So this function is in HAL GPIO.c. Basically, it's a driver file, the GPIO driver file. And the driver file does a callback. Here it is. And this callback, exactly like we discussed in the timer case, we have to implement this callback function in our user application by removing this weak linkage attribute. Let's do that. Let's go to the main.c. So let me just remove these codes for a time being. This was our period elapsed callback for the timer, and let me keep this callback here and let me remove the weak attribute. And here we will toggle the LED. Here we are toggling 3 LEDs, so I'll just remove one LED from here. Let's say red LED. I'll just cut this code and I'll paste here. So the timer will toggle these 2 LEDs, and whenever the button is pressed, this LED will be toggled. Let me save this. Let me just debug this project. So I have my ST-Link external debugger connected to my board. I'll just go for debugging this code. Here I'm getting some errors. This was related to some other project, so I'll just click OK here. Now the code is downloaded onto the target, and now let's first keep one breakpoint in the it.c. Let's go to the it.c and let's keep a breakpoint here. Let's confirm when we press the button whether this IRQ handler is executed or not. Let's confirm that. Code is not running, so let me run the code first. The code is running now, and now let me press the user button right here. Yes, as you can see, the program execution came inside the IRQ handler and it halted here. That means our interrupt configuration was correct. Now let me remove this and let me just run this code, and as you can see, whenever I press the button, the red LED indeed toggles, and these 2 LEDs are toggling because of timer interrupt. Alright, so that's it for this lecture. I'll be back with another project in the next video. So if you found this helpful, please like, share and subscribe to our channel. And thanks for watching.